Session. And the first speaker is Gong Chen. Good morning. So I'm going to thank the chairman for the introduction and also thank organizers for having me here. So in this talk, I'm going to show you our recent efforts using mainly real-space imaging technique, which is followed by low energy like microscope to explore these structures on the surface of using methods and software. And in the second part, I will show you using X-ray scattering, which allows us to determine if the sample has a chirality or the sign of the DMI. So thanks for the speaker that I will just picture my talk within this interfacial DMI in the thin film systems, and the technique that I will introduce is only available in two places on this planet, so I'm not sure that many people might know. So this is being followed low energy, like a microscope that located in Berkeley Lab. So this is a building and this is a microscope. So this powerful technique that allows you to know the three-dimensional structures. So basically, you will be able to control the spin polarization directions of the incident electrons. And the contrast to that is only a component that will be the parallel or anti-parallel to this polarization direction. So you can basically do X, Y, Z. So here I show you an example. You have this infinite type of strike domain. You have the Y type contrast. This is in polarization direction, and you can locate this in polarization direction magnetically where you have this gray domain and the other thing that is here with the strike domain. So what you can do is you can combine the images into one compound image where on this arrow give you the local polarization spin blocks. How it works is you can shoot the spin polarized electrons with extremely low energy, only a few eV above the function, so it's extremely surface sensitive. So you can jump to the surface and go back to get one image. You can switch the spin polarization direction, spin down to get another image. And you can take the difference between two images, where you get this pure magnetic contrast, where all contribution from that topology will be erased. So the spatial resolution is at order of 10 nanometers. And another nice thing for this technique is allow you to roll the film while you're doing the image. So here I'll show you an example. We were growing additive films on top of the 200 nickel uncovered, where you can see this oxygen sensitivity is without a component of this classical stripe domain. So the width of stripe domain is shrinking because the effective anisotropy of the system is going towards the intent. And now you see it's the grid, and it's all spin going to all intent, so you can see any contrast with all of it. And now I'm going to go to the first little story, where I show you this summarized table from the review paper written by Dr. To see all of this thinking system. In most of the case, people need external magnetic field to shift the energy landscape between spiral and experiments, either to help to stabilize experiments or to stabilize experiments. And our idea was, if we can use interlayer exchange coupling as a virtual magnetic field to help to stabilize experiment phase. So we knew already if we grow iron nickel bilayer on top of hole 1, and you get a strike place with Chiral wall, it's like all this in spiral. And with a correct temperature and a correct amount of the field, you would expect that you might stabilize the experiment phase. But alternatively, you can also first put a layer, magnetic, automatic type single domain, in this case it's nickel, and you can put non-magnetic spacer layer, which is copper here. Then you can put iron on top. And we tested systematically the spin configuration on top of the surface as a function of the copper thickness. Then we found that the copper is 14.6 monomer, that's the strike base, there seems no strong virtual magnitude, but the copper is to 8.6 monomer, that is the buffer phase. There's another data that I don't show today, but when copper is to around 5 monomer, that's single domain, that this ratio, the virtual magnitude is so small that the skin structure is single domain. So the fact that this skin configuration is extremely sensitive to the thickness of the copper indicate that the interlayer is incompetent is playing a role, whereas the straight field out of the nickel might play a minor role, might not play a role. So now we can take advantage of a spleen. So we got the bubble phase and we turn this improvisation to implant. Now we get the implant sensitivity where we get this white contrast indicates the implant component within the circuit. So you can select one that you like. You can color code this into one image. So to show that more clearly, you can convert every 3x3 pixel into one array-based data. So no, this is not a sketch, but this is real data, which clearly shows you this is hedgehog skirmion's without field at room temperature later. There was this theoretical paper by Sam Bugle where we make this case more general in other choice of materials. And now I want to go to the second little story where instead of having this SNC001 interface, which I will call isotropic interface, but in some other interfaces with lower symmetry, the DMI will be anisotropic. But there might be another term that you cannot avoid, is the unixo anisotropy coming from the rows in this active film. So what you might expect is instead of having this isotropic skyrmion, the infant component of the skyrmion might be twisted along the ethers of the anisotropy. So we tested this idea by growing iron nickel bilayer on top of tungsten 110, which is PC110. And this monolith nickel, the lead package shows 1/7 superstructure, meaning there's an axial strain in the system, which might give you a strong anisotropy. And this is the spleen image. If you use microns, so this is a very large bubble, but if you look at the infant component, which is highlighted by this color, you see all this infant component is power to the index of the KU, which is on vertical direction. So this is very similar to the sketch here. So this might be the some type of the skyrmion that's in the presence of this low symmetry interface. And in this workshop, I also see some efforts to stabilize the infant skyrmions with the skyrmion with large infant component, either in this narrow disk with a significant DMI, or in another defined compound with a strain, so up to this large infant anisotropy, where in the middle, exposure showed yesterday is intermine twice domain, and the boundary really, which is in LANL, we have this polygon helical spin spiral as opposed to focal point. So the idea is, can we possibly stabilize such spin configuration that you can imagine around this configuration, you rotate all the spin by 90 degrees, and this spin configuration might end up to this core into my pi, the boundary of my pi. So to do this, we tried some efforts. We chose a system that we knew there's a DMI, so copper nickel, iron on copper, has optimized domain with our network, and include more iron to push anisotropy closer in. Where we see this conventional implant domain, but with a parallel implant network. This is because it has automatic rotation geometry from output to implant. Then you must put the energy turn on the DMI. The cross production between S and SJ will be this green arrow, which will be the power or anti-power to the right of the DMI. If you have the implant rotation sense, which is confined by the residual energy, then the cross production will be normal to the film plane. Therefore, the DMI energy will be always zero. That's the reason why we don't see the parallelity here. So how you might possibly to stabilize all of them components within the boundary. So we propose this idea, and I show you among color simulation-based phase diagram as a function of the effective enthalpy along y direction and the vertical direction. The horizontal direction is the strength of the unix enthalpy. So if the unix enthalpy is 0, you have this conventional rotation transition from in-plane nail wall to out-of-plane parallel nail wall case. But having this state where the energy penalty of having out-of-plane spin will cost much less energy, plus the additional presence of unix enthalpy will make in-plane nail wall much harder because when the spin will take within a plane, it has to go across the hard X of the cube. So these two contributions are all helpful to stabilize this configuration where you have the in-plane domain, but with the out-of-plane domain wall. If this is a cycloidal case, then the DMI might possibly to stabilize the chirality. And we showed along this line the three typical simulation. This is a Chiral nail wall, out-of-plane magnetic domain. This is the in-plane domain, but with out-of-plane wall. And this is the in-plane domain with in-plane wall. And we chose, again, ironing of constant all at 0, and you can simply tune the enthalpy of the system by growing iron. So with different iron thickness, you can not only have these two configurations that we know, but also in the middle, you have this phase, you have this in-plane domain with out-of-plane wall, which fits to the solution nicely. And we also found near this orientation transition, you can find some bubble like this, very similar to the sketch, where in the middle you have this in-plane component as a part of the vortex, and out-of-plane as a boundary. So these two, if you look at the paper, actually we were mainly talking about the domain one, but I saw this is this bubble case might fit to this workshop better. And next, I want to discuss briefly the role of the DMI in the formation of the bubble. I showed you two cases, the same aeronickel film where we knew the DMI can dominate. So you have this very large bubble, and with the Chiral nail wall, so some people call it Chiral bubble. But when the thickness of the film is too thicker, you again have this bubble. And now if you look at the boundary, now it's a block type. If you follow the red arrow or white arrow, you have opposite rotation sense, meaning the system, there's no preferred chirality. So it's important to tailor the DMI if you want to get this chirality stabilized in the system. And what is popular to try to understand how the DMI locates and how you can engineer the multi-layer stacking to enhance the DMI. And we did try to use this ABC stacking, which a lot of people use right now in either iron nickel copper or iridium cobalt nickel, where we show the evidence of enhancement of interfacial DMI by using this Tailoring superlattice. And also French group showed that with optimized structure and transfer interface, we have a much larger DMI, which leads to sub-100 nanometer experiments. I'm going to say this as a starting point for the last part of the talk, but now I want to do something slightly different. So if you look at the periodic table of elements, if you want to have a large DMI, a lot of people want to go to the chemistry metal 5D or 4D. But we found that graphene might also possibly to induce decent DMI in the system. So I first introduced the Chen part, where we chose to grow cobalt on leucinium or one. And this is lead patch on leucinium type. This is high quality crystal. The first, so the 2 molar of cobalt on leucinium will have out-of-plane enthalpy. But due to the strain, the 3rd molar will give you in-plane. So if you choose a fractional area 4.3 as a circular, the system might end up to this stripy out-of-plane in-plane alternating configuration, which is similar to the Smith barrel. And we can quantify the chirality of the system by defining this angle alpha, which is an angle between vector n then it's a normal vector always pointing from white to the black. So if all the spin within the boundary give you alpha is to 0, that gives you left-handed nail. So if alpha is pointing outside direction, that's right-handed nail. If alpha is plus minus 90 degrees, that's possible. So we plot the histogram of alpha. You see that the system is dominated by this right-handed nail. However, when we grow graphene on top of Lucinium, we can down passing in the chamber, heat the sample to between 600 and 900 degrees C. You have this nice Mori pattern that indicates the formation of the graphene. And you can grow cobalt on the graphene and the heat sample again. This interfacial of the cobalt will occur, and we have this single crystal high quality graphene cobalt system. Surprisingly, if you follow the white arrow now, which gives you the sign of the DMI and chirality, now it's pointing from gray domain to the black domain. And you now see this histogram that's left-handed nail. So the presence of the graphene can switch the effective DMI of the system, indicate that there's a significant DMI at the graphene cobalt interface. So we can further quantify the DMI interface. So we first perform systematic thickness-dependent transitional chirality, which allows you to quantify the DMI based on the picture that I mentioned before. So we tested the graphene case. You can see the evolution of this histogram from single peak on left-hand nail gradually to double peak at the plus minus 90 degrees, meaning there's a catalog block. So the DMI is not dominating. And we also do the nickel cobalt modular because if you only put the cobalt in here, the auto can essentially only survive for 2 hours cobalt. So we use the nickel to help to extend the auto can into thicker film so that we can cover the transition from right-handed nail with similar train towards a Chiral block. So with this transition, then it allows us to determine the DMI in graphene cobalt, which is 0.11 milliliter per atom, whereas the DMI of cobalt within the interface is negative 0.11 milliliter per atom. So you do the simple math to know the DMI of the graphene cobalt interface will be 0.22 milliliter per atom. So how can we understand this? My parameters from renewable, they perform this layer resolve or layer dependent DMI. What they did was at platinum cobalt interface, this is platinum and this is cobalt. They found that the DMI energy will be the largest right on top of this adjacent cobalt layer. However, the largest energy difference of this being halfway shows up in the adjacent platinum layer. And we do the same thing for graphene cobalt case. Where similarly for the energy of the DMI, it locates in the adjacent first cobalt layer. However, the energy difference of the spin-off coupling disappeared in the graphene case, and it still locates within the cobalt. That means the model of the first method that proposed many years ago doesn't apply to this case. And so we propose to use the Rashba type DMI, where I don't have time to introduce the detail of the number that's derived, but there's a preprint where they did calculation of the Rashba structure and also Rashba splitting from where they were able to get this data and this number, which is nicely to the experimental data. And from here, I like to kindly ask the staff to turn off the camera. So the motivation is
so we face something called there was after another one time. I think before that it was one or two. No. Yeah, I heard something like that, but then there was one, it was up and the other, and one down, and then there was a configuration there down that.
Not this one.
So this one on the left, you call it a bubble?
Yeah, so to be honest, we were focusing on domain 1, and this is kind of, we saw the bubble formation in your film.
So I mean, what do you call the one on the left?
I'll call it bubble or, if possible, inconspicuous. Inspired by.
I think this must be a Skyrmion and a non-Skyrmion. I don't think it's
So you mean if you consider the white part as a, you consider this part as a form experiment, this part as a form, that is right. Yeah, I see.
just by completing the picture, the vectors around that, you cannot do anything else than Skyrmion. I think this is going to possibility. I'm not sure about that.
Let's complete carefully how to calculate the starting number of this structure.
That should be one.
I see how you.
The structure, in case of the right hand side, it's coplanar here. So they all lie in the same plane.
Yeah, that's pain by the
Pathological charge is
that's something that I didn't discuss in detail, but I think due to
the
the
pathological charge. That's
I think that these things are basing out.
it's a white and black
Are they all coplanar, right? In one plane.
So due to the resolution of the spleen, we were not able to detect the two polynomial point here. But we have newer data that I can show today. We went to another spleen in Japan that allows us to see directly the presence of the global point here. So depending on the vector of the DMI along vertical direction, that will determine the rotation sense along horizontal direction. So in that direction is also Chiral. My feeling is this might be Skyrmion's number 1 configuration.
Did you see Skyrmion's at all with graphing to
We haven't tried that. So you know that the spleen is a mechanical, so that it will be difficult to apply in situ field. We have the multiplicator, but that multiplicator is not high enough to clean this here. So that's the true story. So here, what I showed is only the zero field domain configuration. But I think if there's a possible way that we can clean the routine, but we also use coil, there should be the presence of the Skyrmion, because the interface of the cobalt graphene not only gives you the significant DMI, but there is another paper done by some group. They show that there will be also a strong anisotropy element.
Two things. Yesterday we heard a lot about the refereeing process between Skyrmions and bubbles and the semantics of it.
Yes.
But I would like to say also sometimes the refereeing process works because we submitted this paper which you mentioned, with the interlayer exchange stabilized small Skyrmions, scale Skyrmions, and the referee told me that you are first. You had been first. And I don't know who was the referee, but he is in the room. Thank you very much. You signed your paper and submit it again. So sometimes the refereeing process really works if you have a reasonable referee. But I would like to come to one aspect, the graphene. So we all know that graphene has no spin-orbit interaction. The nuclear number, I think, Z is equal to 6. So you cannot change and generate any micro EV, only micro EV type DMI. And graphene cannot be the source of the DMI. So my speculation is that graphene has some electronegativity and produces a dipole in the cobalt, an additional dipole, a charge dipole, or a charge redistribution, something like some degenerate d orbitals become degeneracy significant. And actually the DMI is in the cobalt and not in the graphene. That is my personal interpretation.
You're right. You're
I
right.
don't know exactly how you think about this.
You're right. You're absolutely right. I share the same truth.
Any other questions? So actually, so you just respond to that, you were also not the first as far as those small terminals, or did I miss
No, he was, I think, the first to use the concept of interlayer exchange coupling to manipulate skyrmionons. And we use that concept. If you have a frustrated magnet, if you have besides here, also frustrating in exchange, then basically the tendency of the skyrmion can become very small. The skyrmion can become very small. But in order to have a spiral, to unwind the spiral into skyrmion, you need an enormous amount of energy, 30 Tesla, 40 Tesla. So the frustration gives you a spiral, a frustration spiral. But you have still DMI. So you can still have the skyrmion. But to unwind this spiral, you need 40 Tesla. Nobody has this in this lab. So therefore, you need this interlayer exchange coupling to unwind this exchange interaction to get the skyrmion. That's what we use. But the concept of interlayer exchange coupling was a few months earlier. I was used by him. And this I didn't catch. And I was technically well.
So since we're in Los Alamos, we have 6,500 Tesla magnets.
You know, I'm thinking a little bit more about that.